Greetings, netizens. The speed of light is a theoretical limit that cannot be matched or exceeded by any object with mass. Only massless particles like photons can reach that limit. Let's imagine that we somehow manage to approach this speed as closely as possible. But what happens if we travel at the speed of light? The universe is strange, but it becomes even stranger when we travel at the speed of light. Now, you will see why. As you know, time and space are not constant as we often believe. The distance between 2 points varies depending on the speed at which we move, and the same goes for the rate at which time passes. It is not always the same. This is the most crucial aspect of traveling at the speed of light and the cause of all the bizarre effects we will see next. However, let's mention right away that it is impossible for us to travel at the speed of light because, according to Einstein's equation, it would require infinite energy. So, let's assume we possess a fantastic technology that allows us to travel at 99% of the speed of light, and we are aboard a spaceship. What do we feel when we travel at the speed of light? The truth is that we wouldn't feel anything. One of the oldest principles in physics and Galileo's relativity states that it is impossible to feel motion or determine whether we are moving or not. This means that as long as we don't accelerate, it doesn't matter how fast we move, we won't have a sense of speed. Nor can we conduct any experiment to know that we are traveling at the speed of light. That's why the effects must always be compared with another person or object, for example, someone staying on Earth. Right now, all of us are moving at an enormous speed through space, yet we don't notice it because the velocity is constant. We are rotating at 1,670 kilometers per hour and orbiting the Sun at a speed of 107,208 kilometers per hour. At the same time, the Sun is moving through the galaxy at 792,000 kilometers per hour. But it doesn't end there. The entire galaxy is in constant motion through the universe. The Milky Way is heading towards the Andromeda Galaxy at a speed of 468,500 kilometers per hour and is also traveling towards the Hydra constellation, the Great Attractor, at approximately 2 million kilometers per hour. If we add up the rotational and translational velocities of the Earth, the speed of the solar system, and the motion of the galaxy, we reach a figure of around 3.5 million kilometers per hour. That's the actual speed at which we are moving right now, and of course, it remains constant. If the Earth were to suddenly stop rotating, we would all be in for, well, let's just say it wouldn't end well. Those who didn't get crushed would be launched at speeds exceeding 1,000 kilometers per hour, surpassing the speed of sound. Then, all the people and buildings would fall back somewhere on Earth. There would be hardly anything left of us, and that would be in the best-case scenario. But let's get back to the speed of light. Let's assume that we reach the speed of light with a smooth acceleration to avoid death from excessive acceleration. To achieve this, we would need to accelerate for a year until reaching nearly 300,000 kilometers per second. In many science fiction movies, we see spaceships accelerating suddenly without considering the physical consequences of inertia. Therefore, the spacecraft would need to have a highly developed system to eliminate inertia. If we were to build a spaceship with infinite energy and without inertia, we would encounter other problems. The primary obstacle to interstellar travel is not the technological aspect, which we could master in a matter of centuries, but the dangerous space environment, as well known by astronauts, once again highlighting the frailty of the human body. If we were to travel at almost 300,000 kilometers per second through outer space, we would die within seconds. While the particle density is very low in the vacuum of space at high speeds, the few hydrogen atoms per cubic centimeter would impact the spaceship's front with an acceleration similar to what is achieved in the Large Hadron Collider, resulting in an energy of 10,000 sieverts per second. Considering that the lethal dose for a human is about 6 sieverts, this radiation would damage the ship and destroy any trace of life inside. According to measurements by scientists from Johns Hopkins University, no front shield would be capable of shielding us from ionizing radiation. A 10-centimeter thick aluminum partition would absorb less than 1% of the energy, and its size couldn't be increased indefinitely without compromising the energy requirements of the propulsion system. Additionally, the spaceship would have to withstand erosion from interstellar dust, significantly increasing the likelihood of its structure being pulverized. As a solution, we would have to settle for reaching speeds of only 10% of the speed of light in a generational ship, allowing us to travel to the nearest star, Proxima Centauri, within a human lifetime. The 4.22 light-years distance would turn into a 40-year journey. But let's suppose we have also managed to build a spaceship with super shielding and a technologically advanced shield that nothing can surpass, not even radiation. We travel at the speed of light and have a friend who remains on Earth and serves as our reference. The difference between our time, space, and theirs would lead to very curious situations. time and space change when we travel at the speed of light. When we travel at nearly the speed of light, time passes much more slowly for us than for our friend on Earth. We won't notice it, our clocks will appear to be ticking at the same speed. However, when we return to Earth, we will see that our friend has aged much more than us. After 9.5 months of traveling at 99.9999% of the speed of light, we find that over 56 years have passed on Earth. 3 important things happen when we travel at speeds close to that of light. First is time dilation. At almost the speed of light, time runs slower for us, but interestingly, we wouldn't perceive this change. For example, 10 minutes on our spaceship's clock might correspond to 11.6 hours for observers on Earth. In other words, every second on our ship is equivalent to 70 seconds for our friend on Earth. The second effect is aberration, which causes our field of vision to contract into a narrow tunnel-like window. The third effect is the Doppler effect, where light waves from visible stars get compressed, causing space objects to appear blue with a flash of light, while stars behind us spread out and look reddish. As you increase your speed, the visual experience becomes so intense that everything seems to fade away. It's essential to understand that this doesn't mean we perceive reality distorted by a flaw in our senses, but rather that when we travel at the speed of light, distance and time genuinely vary. Hundreds of experiments have confirmed that these effects are real and measurable, not illusions or mathematical tricks. Therefore, even if we could build spaceships that approach the speed of light, we would face a significant problem with time. The rest of the universe would be moving much faster, as we've seen, and time only slows down when we travel at high speeds, especially near the speed of light. For a crew traveling in a quasi-lightspeed spaceship, they might cross the galaxy in a few decades, but during their journey, over 100,000 years would have passed for the rest of the universe, which isn't moving at the same speed. Consequently, when the crew returns to their home planet after completing their mission on the other side of the galaxy, all their loved ones would have died long ago. And the world might be unrecognizable, depending on how much time they spent wandering through space. This makes traveling in such a spaceship a one-way journey, not an especially attractive scenario for astronauts who plan to reunite with their family and friends. However, theoretically, we could use this method to send unmanned missions to the other side of the galaxy. Avoiding the problems and risks associated with life support systems, such as suspended animation for thousands of years or building a generational ship where the descendants of the original astronauts reach the destination. Undoubtedly, the vast universe may seem too big for our slow ships right now. But there will come a day when we discover alternative energies and technological advances that we can't even imagine. If we are prepared for that, our future will be to sail among the stars. If you enjoyed this video, give it a like, don't forget to subscribe, share it on social media, and leave your comments below.